One of our major classes of reactions are oxidation-reduction reactions. Oxidation refers to an atom losing electrons, and we use our little mnemonic here, which I'll show you in a minute. And reduction is gaining electrons. So an example of a chemical reaction where this is super clear is a reaction of magnesium metal with hydrochloric acid to make hydrogen gas and magnesium chloride. And we'll balance that with 2 there. So on the reactant side, the magnesium is in its elemental neutral form, and at the end of the reaction, we know that this is an ionic compound and the magnesium is in its Mg2+ form here. And this is a soluble compound, and so it's even aqueous. So in this case, the magnesium in its neutral state would be an oxidation number of 0, and if it goes from 0 to a +2, it's losing 2 electrons, and this would therefore be oxidation. And on our reactant side, we also have hydrochloric acid. We know that this is another sort of an ionic compound. It's an acid, and the H is as H+. And then here, the hydrogen gas is in its neutral elemental state here. And so that one also has an oxidation number of 0. And so when two H+'s go to H2, these are gaining 2 electrons. And the 2 electrons that are lost by the magnesium are balanced out by the 2 electrons that are gained by the hydrogens. And so between these two, oxidation and reduction happen. And it always happens as a pair. One species, or it could be more than one, but usually it's just one species gets oxidized and the other species gets reduced. So our mnemonic devices here, you probably have seen these before, and there's a couple of different ones. I usually go with oil rig. So oil rig stands for oxidation is loss of electrons, and reduction is gain of electrons. You also might be familiar with Leo Gur. And so that just turns it around. Loss of electrons is oxidation. Gain of electrons is reduction. So in order for us to recognize when an oxidation and reduction reaction is taking place, we have to be able to identify the oxidation numbers. I've already sort of shown you a few oxidation numbers, but we're going to go through this in detail in case it's been a while since you have seen them, or in case this is your first time having this broken down. So we have several rules for identifying oxidation numbers. So I'm just going to go ahead and lay them out. The first rule I mentioned is that all elements in their pure elemental state have oxidation number of 0. I should probably put pure elements here. If you have something that's in an ionic compound, so all monatomic ions, like we had in HCl or NaCl or something like that, they all have the oxidation number that is equal to their ion charge. So just as we know that sodium here is +1 for its charge, and chloride is -1 for its charge. The same thing is true about their oxidation numbers. Sodium would have a +1 oxidation number, and chloride would have a -1 oxidation number. So this covers most of our metallic monatomic ions anyway. And then we also need to deal with our nonmetals. So when we're talking about our nonmetals, we're going to have a short set of rules for dealing with nonmetals, and then we're going to have to figure everything else out from there. So I have 3 nonmetals that I'm going to talk about. The first one is fluorine, and fluorine always has a -1 oxidation number. Incidentally, it's always an anion with a -1 charge, unless it's in its pure elemental form. Our next one is oxygen, which gets a little bit complicated. So oxygen is usually -2, but we have a couple of exceptions. So our first exception is in a peroxide. So the peroxide that's most familiar to people is hydrogen peroxide, H2O2. And so in peroxides, we'll actually get to the hydrogen rule here in a second, our H is still a +1 oxidation number, and so in order for these to balance out their oxidation numbers and have a net charge of 0, the oxygen has to be a -1. And then we have another really crazy case, and these guys are called superoxides. These are extremely rare, so you're unlikely to actually encounter any of these, except for in like a exercise, a homework assignment potentially. So a superoxide has a +1 cation, like potassium, with 2 oxygens, and the potassium, this goes back to our rule number 2, right? All monatomic ions have their oxidation number equal to their ion charge. And the potassium has an oxidation number of +1. So in order to balance that out, the oxygen actually has to have a -1/2 because there's 2 of those oxygens. So this is kind of one of those crazy examples. But I wanted to be complete and tell you all of them. So finally, we get to hydrogen. And hydrogen is almost always +1, as we have seen a couple of times. The only time when it isn't is if it is acting as an anion in an ionic compound, which is only going to happen if it's bonded to a metal as the anion. So that might be something like CaH2, calcium hydride. So because calcium is +2 for its ion charge, the hydrogen is going to be -1. And that's our only other option. Okay, so our final rule here is that if you have something unusual, for everything else, including for polyatomic ions, we're going to use the rules above and the total charge for example on a polyatomic ion to calculate the missing oxidation numbers. So an example here might be something like, how about sodium nitrate? So when we look at sodium nitrate, we're going to separate it into its ions first. So we know that this is sodium plus, and that's a cation. And so its oxidation number is going to be the same, +1 for the sodium. So for the nitrogen and the oxygen, this is nitrate ion, which has a -1 charge. I will remember my oxygen has a -2 charge unless it's in a hydrogen peroxide, or excuse me, in a peroxide or a superoxide, and that's not what's going on here. So I'm just going to figure out the nitrogen from everything else. So I'll write up a quick little equation, and I'll say nitrogen plus 3 oxygens, which are -2 each, gives me a total of -1 charge. So 3 times -2 is -6. And if I add 6 to both sides to get the nitrogen on one side by itself, then I'm going to have 6 minus 1. And so that's going to be a +5. So the oxidation number on my nitrogen is going to be a +5. And when I write my oxidation numbers for each element, I don't write it multiplied by any subscripts. I just write it for a single element. So we can do examples with a single compound, but if we're talking about an oxidation-reduction reaction, we're going to want to be able to identify all of the oxidation numbers for the elements in a reaction. So let's look at a couple more examples here. Let's look at the reaction of burning methane in air. And we're going to assume it reacts completely to form carbon dioxide and water vapor. So our first question might be to assign the oxidation numbers for all of the elements. So what I usually do when I assign oxidation numbers is I'm going to separate things out by compound, and I'm just going to work my way through them. Okay, so if I look at CH4, I'm going to start with what I know. I'm going to know that hydrogen is +1 because this is not an ionic compound, and so hydrogen is not the anion here. So in order to be neutral, this has a total of a 0 charge, which means that if I have +1 multiplied by 4 plus carbon equaling 0, that means my carbon has to be equal to a -4 in order to cancel out. For O2, I know that the oxygen is 0. I'm going to put a little slash through that, or I'll just write 0 here to be really clear so that we don't get it confused with the O, because it's in its pure elemental form. So carbon dioxide, we're going to again start with what we know, and we know that oxygen is usually -2. So if I have 2 of those -2s plus carbon, and that's a neutral compound, then my carbon has to be a +4 in order to neutralize that. And then our final compound here is water. And you can start with either element here. Oxygen is a -2, hydrogen is +1, and everybody is all set. So our next question might be, what is oxidized and what is reduced? So if I look at my oxidation numbers, what I'm really looking for is, I'm looking for change. So over here I have a hydrogen that's +1, and here I have a hydrogen that's +1. Nothing changed there. Here I have a carbon that's a -4, and now I have a carbon that's a +4. So carbon did change. carbon went from a -4 to a +4. What else? Something else has to change. When I look at the oxygen, oxygen starts as a 0 here, and then it goes to a -2. So that's my other change. We went from a 0, that's going to be a little awkward. Let's do a 0 like that one. And then it went to a -2. So each of these two changes, when I went from -4 to +4, I am losing negative charge here, so this is oxidation. And when I go from a 0 to a -2, that is increasing the negative charge, which means that the oxygen was reduced. Oh, I wrote oxidation, so we'll write reduction here. Okay, so you might have thought about oxygen and how oxidize and oxygen sound really similar to each other. And this is really true. It's probably where the term oxidation comes from. And that is that oxygen in a lot of reactions will go from a 0 to a -2. It'll be reduced. And that means that oxygen oxidizes the other thing. So oxygen, or in this case, the thing that is reduced, I don't need a comma there, is called the oxidizing agent. It is the thing that made the other thing get oxidized. Okay, so they're kind of opposite. If it got reduced, then it oxidized the other thing. It was the oxidizing agent, and vice versa. So the thing that was oxidized is the reducing agent. So when we have a straightforward gas phase reaction like we just did, everything is all balanced and it's really easy to see what happens. But you might remember that we also talk about half reactions in redox reactions. And sometimes when aqueous reactions that are redox reactions are written in our books, they don't include every single part of the solution that's there. And so sometimes we are also asked to balance redox reactions, and we use the half reaction method. All right, so we're going to go ahead and take time to go through this as an example. So I'm going to just go ahead and start with an example, and then we'll see those steps illustrated as we go through the example. So the example here would be maybe to balance the reaction of nickel oxide, which is probably a solid, with iron metal, so that's also going to be a solid. And it's going to turn into nickel hydroxide, which is probably aqueous, and also iron hydroxide. And we are told that this is in a basic solution. That makes good sense, right? We're making a bunch of hydroxides here. So, okay. So our first step when we are balancing using the half reaction method is that we have to identify what is being oxidized and what is being reduced. And so I'm going to assign oxidation numbers to figure that out. Plus, it's good practice for us. If you want, you can pause the video and you can go ahead and assign oxidation numbers and then check your work here in just a second. Okay, so here I go. Nickel oxide. I know that my oxygen is probably going to be a -2. So the nickel will be a +4. Iron is a pure elemental form, so it will have a 0. Nickel hydroxide. I know that the OH- ion has a -1 charge, so my nickel is going to be +2, and then oxygen will be -2 as usual, and hydrogen will be +1 as usual. And you can notice that -2 + 1 will equal -1. And the iron hydroxide looks exactly the same as the nickel. Where we have oxygen as -2 and hydrogen as +1. So if I look at identifying what's oxidized and what's reduced, once again, I want to look at the changes. So if I look at oxygen here, it's -2, -2, -2, that didn't change. Nickel, +4 right here to +2. Okay, so this did change. And if I go from a +4 to a +2, I do that because I added 2 electrons to become less positive. So gaining electrons, that's reduction. So the nickel is reduced. And the oxygen, or excuse me, the iron goes from a 0 to a +2. And so it's losing 2 electrons, and it must be oxidized. And if we look at the hydrogens just to check, we can see that those guys didn't change either. All right, so we've identified what was oxidized and what was reduced. The iron was oxidized, the nickel was reduced. So we're ready to move on to our step 2, which is to separate into half reactions. And the half reactions, these are the thing that was oxidized and the thing that was reduced. So I'm going to take the iron part, and then I'm going to take the nickel part, and I'm going to separate them from each other. So my nickel oxide turns into nickel hydroxide in one half reaction, while the the iron turns into iron hydroxide as well. Okay, so our step 3 is to balance the elements. And when we balance the elements, we also need to pay attention to oxygen and hydrogen. So we need to remember that to balance oxygen, we're going to add water. And to balance hydrogen, just elemental hydrogen, we're going to add H+. All right, so let's look at reaction A. Our nickel oxide is turning into, I'll leave myself some space, nickel hydroxide. So let me count up. I've got 1 nickel, 2 oxygens, 2 oxygens. Now I have 2 hydrogens and no hydrogens. So to balance the hydrogens, I'm going to add 2H plus on the left-hand side. Okay, so reaction B, I have iron, and it's turning into iron hydroxide. So over here I have 1 iron, over here I have 1 iron. Here I have 2 oxygens and no oxygens, so I need to add 2 waters because each water has 1 oxygen. Now I have 2 oxygens and 2 oxygens. Over here now I have 4 hydrogens, and here I have 2 hydrogens, so I'm also going to add 2H plus to balance out the hydrogens. All right, I've now balanced all of my elements. I'm ready to move on to the next step. So this is a step that's different from all of the other balancing that we do, because here we need to balance the charge. And the only tool that we have is electrons. We want to have the same charge on each side of each half reaction, so we're going to have to add electrons to balance that out. So for reaction A, I'm just going to go ahead and rewrite this again, but I'm getting lazy. I'm going to stop writing the phases. Oops. There we go. Okay, so nickel oxide has 0 charge, and we have 2 hydrogens over here, and so we have a +2 charge on the left-hand side, and over here on the right-hand side we have a 0 charge. So in order to make both sides of this reaction have 0 charge, I need to balance out those +2. So I'm going to add 2 electrons to this side to make both of these equal to 0. Now our other reaction, if we look at our charges there, over here we've got no charge, no charge, no charge, +2. So just as we did before, we need to -2 by adding 2 electrons to get over to a 0 on this side too. All right, so when I balance the charge, I also need to now check the balance of the charge between my 2 reactions, and that's step 5. So here I have 2 electrons and 2 electrons. Those are the same, so this is already balanced. But you can imagine a scenario where maybe one of my reactions was 2 and the other one was 1. And in that case, I would take the entire reaction that had a 1 and multiply the whole thing by 2. And I would just double it to make the number of electrons that were coming out of that reaction the same as the number of electrons that were going into the other reaction, or vice versa. So we can move along to step 6 already. And step 6 is to add the reactions together and cancel things out. Okay, so if I add these guys together, I'm going to get 2 electrons plus nickel oxide plus 2H plus iron plus 2 waters. That's everything that's on the left-hand side of my arrow. And then I'll have nickel hydroxide, iron hydroxide, 2 hydrogens, and 2 electrons. Now, if you've done it right, your electrons will cancel. And that's one of the ways you can know that you've done it right. Because the number of electrons that are going into one half reaction have to equal the number of electrons that are coming out of the previous half reaction. So here I can also cancel 2 hydrogens on each side, and then that's it. So when I finish up, I'm almost done here. The final reaction, or the final steps, excuse me, is that if we are balancing in a basic environment, we wouldn't be able to have any H pluses left over. So in a basic environment, we would add OH minus to each side to balance any H pluses. So here my H pluses canceled, I don't have any, I don't have to do anything. And my final reaction is just this nickel oxide plus the iron plus water makes nickel hydroxide and iron hydroxide. And then we are done. Hopefully this was a good reminder of how to balance redox reactions, or if you're seeing this for the first time, hopefully you have a pretty clear sense for how to do it. As always, please feel free to ask for more examples or more help if you have any additional questions.